Hey, it's Mr. K. Let's talk about covalent bonding. Covalent bonding happens between nonmetals. This is different than ionic bonding because we are sharing electrons. Your Lewis model should include lines, not arrows, to show the electrons are being shared, not transferred. These do not have fixed ratios. They can be very interesting, very cool. That's why we need prefixes. Please don't use charges. Okay, now let's talk about a little bit of terminology. First of all, these dudes right here. In your Lewis model, if you have a pair of electrons, this is called a lone pair. This thing takes up space when we start talking about shapes later on, but right now it just means that these are already paired up. They do not want to bond. However, if I look at carbon, it has 4 single electrons, and as such, it has 4 locations where it can make bonds. So in order for carbon to be happy, we're going to see it make 1, 2, 3, 4 bonds. And those could be 4 singles, 2 doubles, maybe chuck in a triple. Who knows? As long as there are 4 bonds on each carbon, that carbon is happy. For nitrogen, we have 1, 2, 3 bonding locations. So that means that nitrogen is going to make 3 bonds, whatever that may be. Any of these combinations, for example. With oxygen, we have 2 single electrons, so we have 2 bonding locations. Oxygen can either make a double bond or 2 single bonds. And then finally, fluorine just has 1 sad little bond. So what you're going to do is you're going to find fluorine at the end of molecules as it is terminal. It can only be at the end, it cannot be in the middle of a molecule. Now looking at these, leads to another point, that is that carbon, because it can make so many bonds, is responsible for a lot of compounds in nature. In fact, it has its own area of study in chemistry called organic chemistry. All of our living things are based off of carbon. Some science fiction novels, or even Star Trek, talks about silicon-based life forms on other planets. We are carbon-based life forms, and silicon also has 4 bonding locations, so maybe on some other planet there's silicon-based life forms. I don't know. My high school teacher said it. I thought it was cool, so I've been saying it for 100 years. Okay, let's do an example. Let's do carbon, and let's do fluorine. That's right, my pen erases. You should be jealous. So here's carbon. Now, carbon can make 4 bonds, so I'm going to put it in the center. It's going to be what I call my central atom. Fluorine, like we just talked about, can only make 1 bond, so it's going to have to be on the edge. What I see here is that these two can share those 2 electrons. In order to make this thing work, I need 4 fluorines for a simple molecule. And I end up with CF4. Okay, another one, very common, that most of you already know the name of, is carbon and oxygen. So again, carbon can make more bonds, so I'm going to put it in the center. Oxygen can only make 2 bonds, so let's put it on the outside. And what I see here is that these 2 electrons, or bonding locations, can pair up with each other and share. This is what we call a double bond. Another oxygen is going to solve this molecule for me, and everyone is sharing. So a couple different ways to show these to represent the sharing is, if I think about my carbon, I can think about these 2 bonds more like this. And then oxygen here. So basically, instead of drawing the lines, I'm saying they're sharing 2, 4, 2, 4, 2, 4, 2, 4. And then I can draw circles to show that every atom now has a total of 8 electrons. That's how this sharing works. This is just another way of getting to that noble gas configuration, or of having a full outer shell. A couple other things to go with here. I think I've got one more for you. Let's do something fun like HCN. Okay, so just looking at this one, I would have my carbon, my hydrogen, and my nitrogen. Now looking at this one, you can see bop, 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 a single and a triple. I can clean that up and write it like this. Okay, now in terms of the way we write these formulas, there is no determinate way on how we state the formulas in terms of what the order is. But with covalent compounds, sometimes the order will help us determine the shape. So occasionally, if you're given hints in the way the formula is written, it's meant to help you draw the shape. Secondly, there's another way. There's something called electronegativity. With ionic compounds, we always write the positive, then the negative. Here, we write the one that has a larger pull on the electrons. So the more electronegative, usually second. However, some compounds break that rule. What can you do? All right, thanks a lot for tuning in.